Lesson 7-7, Exponential Growth and Decay. So again, we're working with our exponential functions, which we learned in the last lesson. That can be written as y equals a times b raised to the x power. However, with these functions, sometimes things are growing exponentially and sometimes things are decreasing, or we call it decaying exponentially. So we're going to explore both of those. So if something is growing exponentially, exponential growth, the graph would look something like this. It would be going up positive to the right. It can be modeled by the function y equals a times b to the x, which we learned in our last lesson. However, the growth factor, which is our b, our variable b is the growth factor. In exponential growth, the growth factor equals 1 plus the percent rate of change expressed as a decimal. If something was growing 25%, we know that that decimal is 0.25. Our growth factor would be 1 plus that percent. So 1 plus 0.25 is 1.25. That would be the value of b in a growth factor exponential growth function. Okay, so here it is with algebra. You want to make sure you have this written down. Y equals a times b to the x. That's our function. A represents the initial amount when x equals 0, when x hasn't grown at all. B is the base, which is greater than 1. It has to be bigger than 1 to be a growth factor. And x is our exponent. Okay? For example, in our last lesson, we talked about the beetles that were reproducing every couple weeks, which was our x value. They started at 30, that was our initial amount, or the a value. B was that growth factor that's greater than 1. Okay? So, let's try an example. Since 2005, the amount of money spent at restaurants in the United States has increased about 7% each year. There's our increase percent or rate. In 2005, about $360 billion was spent at restaurants. If the trend continues, about how much will be spent at restaurants in 2015? All right, so here's our exponential function. We're going to plug in values for all the variables. X is the number of years since 2005. Well, we want to measure 2015. Our x value is going to be 10 when we plug it in, because it started in 2005. We're going to 2015. That's 10 years, okay? So y is going to be the annual amount spent at restaurants in billions of dollars. So the y will give us how much money in billions is spent as it grows in 2015. The a is the initial amount spent when we first measured, so 2005. So our initial amount was $360 billion. And b is the growth factor, which is 1 plus that percentage that it's going up. The rate is 7%. That's a decimal of 0.07. So our growth factor is 1.07. So I'm going to write the whole equation. Y equals initial amount of 360 times the growth factor 1.07 raised to the x, and in our case this x value is going to be 10. 360 times 1.07 to the 10th power. So what this says is 2015 is 10 years after 2005. That's what we're finding. When I plug this into my calculator, I get about $708 billion spent at restaurants in the United States in 2015 if this trend continues. Okay? So just plugging in all the numbers for our exponential function. All right, now on the flip side is exponential decay. Notice the graph goes down as it moves to the right. So same thing, it can be modeled with a times b to the x, that function rule. However, the base, the b value, is the decay factor, not the growth factor, which equals 1 minus the percent rate of change, okay? So 1 minus the percent. Same thing, y equals a is your initial amount, b is between 0 and 1, okay? So in the last growth factor, it was always greater than 1. With a decay factor, it's always less than 1. Let's do an example. Kilopascal is a unit of measure for atmospheric pressure. The atmospheric pressure at sea level is about 101 kilopascals. For every 1,000 meters increase in altitude, the pressure decreases about 11.5%. What's the approximate pressure? So we're going to write this formula. Y equals, A is our initial amount. Initial amount is 101 kilopascals at sea level. So 101 times. B is our growth factor. Remember with decay, not growth factor, our decay factor. With decay, it's 1 minus the percent as a decimal. So I'm going to divide by 100, 0.115. 1 minus 0.115 is going to be 0.885. Oh, not an exponent, sorry. 0.885 raised to the x power, which we want to know at 3,000 meters, and we measure for every 1,000, so x is going to be 3. When I plug this into my calculator, I get about 70. So the pressure at an altitude of 3,000 meters, is about 70 kilopascals. All right. The final example isn't decay or growth exponentially, but it's talking about compound interest, which uses a very simple formula as our exponential function. So compound interest, when a bank pays interest on both the principal and the interest an account has already earned, the bank is paying compound interest. Compound interest is an example of exponential growth. What they mean is when you put money into the bank charges you interest for how long you keep that money in the bank. Compound interest is when they're paying interest on both the principal, that means the money you put in, and the interest already being charged to that principal. It's paying compound, it's paying even more interest, okay? So this formula for finding compound interest is this right here. A equals the balance of money, the total balance. How much do we need to pay? P is the principal. If I put $200 into my savings account, that's my principal. R equals the annual interest rate. So that R is right up there. Some people get like 7% interest or 4.5% interest. Okay, so you put that as a decimal. N, notice on bottom, and it's in the exponent, is the number of times interest is compounded per year. So some banks will only compound your interest twice a year. Some will do it every month, so 12 times a year. It can change. Whatever that number is, and we'll give you it in your problem, you put in for N. And then T is the time in years. So let's say it compounded your interest 4 times a year. N would be 4, and T would be how many years are we solving for. Let's do an example. It might be a little easier to see these numbers plugged in. Suppose that when your friend was born, your friend's parents deposited $2,000 into an account, paying 4.5% interest, compounded quarterly. Right there, quarterly means 4 times a year. What will the account balance be after 18 years? Okay, so here's our formula. We want to know the amount, the A. Principal, how much money did they put in originally? $2,000. Multiply that by 1 plus. R is the percent of interest. 4.5 was the percent interest. We need to put it as a decimal, so it's going to be 0.045 over N. How many times does it get compounded a year? 4, because it's quarterly. Raised to the N times T. N is 4 times T. How many years? We want to know how much money she'll have after 18 years of that money being in the bank. So 2,000 times 1 plus 0.045 over 4 raised to the 4 times 18th power. When you plug all of that into the calculator and make sure you remember order of operations, it is about 4475.53. So that's how much money the parents, when they put in that $2,000, 18 years later, the money will be up to this amount. All right, so using that example, rewatch if it didn't make sense. I'm going to leave you with your lesson check. 5 problems to try. Pause this, go back and rewatch if you need to.